not say anything. Okie dokie, so we're back. And we're going to do a little bit more of the, let's say, other reactions that come out of these chapters 6 here. Learn a little bit, learn a couple other elimination and substitutions. Learn a couple other substitutions and eliminations as we finish our way up for the semester here. So, there it is. So to get things kind of started, okay, so tell me what reaction happens here. And tell me what reaction happens here. And tell me what reaction happens here. I think you guys got the idea. All right. Call him. Where are you?
I think she's coming.
Bonus points for everyone who's here right now. Right. Everyone who's watching online, forget it. Not an AOH, an ACN. This for a second. Hmm? That's true. You guys do know. you get to that? Mm-hmm. Where's it from? How'd you get that? You just guess it. Is that how science works? I would draw it out, because that is one of the important questions. I have to figure out whether it's a good nucleophile or a poor nucleophile. Don't guess at it. Draw it out. We need to invent masks with beards on them so you can,
Yeah.
so you can do the properly. I'm telling you, I had my $1 million idea though, right? It's easy, just sell t-shirts that have like the masks already built into them, right? Right? Why am I wasting my time here? Organic chemistry, screw that. Exploiting a pandemic. All right, guys, so talk to me here. What do we see? Let's start with the second one there. Because I think I tricked you guys good with the first one. My favorite thing in life is I wake up, I remember how grumpy I am, and I say, what can I do to make somebody else's life miserable? I said, well, my students are forced to listen to me and laugh at my jokes, so that's kind of good. Well, how else can I ruin their days? Right? I give them tricky questions, right? Tricky questions. Now let's take a look at the second one there. So, let's build a case, right? What do we see in the second one there? Okay, got a good leaving group. What else? A very good leaving group, right? Very good leaving group. What else?
Strong face.
How did you get that?
Because CN.
Okay, how did you get that the CN is negative?
Because the NA is a spectator.
Whenever we see sodium, what does it do for us?
Nothing.
Mostly it does nothing, but it does something very important. It is a spectator ion, so really its job is to do what? Spectate and make sure that all the charges are balanced, right? Every negative charge that we've ever drawn has to have a positive somewhere. Now, sodium doesn't participate in the mechanism. That doesn't mean it's not there, right? Do you guys catch what I mean with this? Why do I write things like this here? What does this really have around it? Probably a sodium. Got it? Just because I don't write it doesn't mean that we can't just have a minus with nothing balancing it there, right? So you can easily see your O's with a minus charge bound to a sodium, and it doesn't change anything. Got it? But when you guys see a lithium, a sodium, a potassium, that kind of thing, make sure you guys recognize that whatever it's bound to, right, whatever that sodium is bound to has a negative charge on it. Got it? Is that important to recognize? Yes. Is that important to deal with? Yes. Does it give us lots of good information? No. I'm just kidding. Yes, it does. Right? Right? We have to know where our minuses and our pluses are. That's how life works. Okay? That's how organic chemistry works. So when you see this, what you really should be seeing, right, is that. Got it? All right. So what?
This is strong base, but it's also also a strong nucleophile.
How do we know it's a strong base?
The localized kinetic charge.
How do we know it's localized?
Yeah, let's spread it out.
Can't, huh?
Sorry.
You flipped it. No. How dare you use your own book to do things? Where was that real quick? Stalling for time. Dude, I gotta fill like an hour and 5 minutes, man. You know, I'm sitting here and talk. You guys know how much work that is? Page 318. Okay? Keep in mind that some reagents may not perfectly fit into one of these 4 categories: strong base, weak base, strong nucleophile, weak nucleophile, right? For example, the cyanide ion, CN, with a minus charge. It is a strong nucleophile, but only a moderate base. So what might be going on with cyanide? Why would it only be a moderate base?
Has a triple bond.
Which does what?
Spread the electron density?
How could a triple bond help stabilize a negative charge?
There are more orbitals, the electrons can,
Is it resonance? No. Is it electronegativity? No. Is it radius? No. Is it inductive? No.
hybridization.
It's got to be hybridization, right? What's the hybridization in that carbon? SP, right? If you remember, in our notes, very explicitly, right, we talked about how hybridization kind of helps deal with negative charges, right? So we got an SP, hybridized carbon,
Is
negative
this-
charge.
Is SP2?
No, it's SP. Trying to say I'm wrong, Cole. No, it's fine. I want you guys to ask questions. But it is SP hybridized. Okay. So we have a fairly stabilized negative charge, not too great, right? Even the book calls it a moderate base, but it's still a strong nucleophile, a very strong nucleophile. Okay, so now we've got a strong nucleophile, a good leaving group. The leaving group's secondary, not too much sterics around it. What about our nucleophile? Is our nucleophile sterically hindered? No, it's just 2 atoms and they're linear. Hard to get more unhindered than that, right? We don't specify temperature, doesn't really say anything about solvent. Okay. Don't mention anything about concentration. So probably all pointing towards an SN2. Got it? So, I want you guys to draw me the product, the mechanism of the product there for those 2 reactions. This, they don't see me on camera. Nobody wants to watch a whiteboard. They come here for the main event. Oh, wait a minute, that actually might increase viewership if I'm not on there. Oh God, it's horrible, get them off. See, a lot of people worked on their PhDs overnight, skipping steps. Why would that be? So. All right. Whoops. Nucleophile comes in. Leading group goes out. Right? There's that. There's this. Hooray. Right? Cool. I like it. Good?
No.
What?
Wouldn't you, because it's a chiral center, would you have to do an inversion of?
Yeah, if I specify the stereochemistry here, make sure you put it there, right? We can just assume it's a mix of stuff there to begin with, so we'll get a mix of the products. It is important to pay attention, especially with SN2s.
Okay.
That is always, always, always something important. So what's the product here then? It's just going to be the same, right?
Once the OH separates, it's a strong base. Will that make another reaction then?
Ah. So, looking at the top reaction, okay? Let's build our case for what happens. With the CN minus, we've got a strong nucleophile, moderate base, unhindered base. What about in our other substrate there? Do we have a leaving group? No. Have we ever seen OH minus act as a leaving group? No. Will it ever act as a leaving group? No. So is a reaction going to happen? No. I know. Did I though? Is it tricky, or isn't I just asking us the same questions I always ask? If you guys don't see a leaving group, guess what will not happen? Anything involving a leaving group. Got it? If it's not there, it's not there. But Dr. H, I hear you say, I really want to react that oxygen. I really, you don't understand. I was born for this. I have to make it act as a leaving group. Too bad. Alcohols are not good leaving groups. Let me back you guys up for a second. Why is I minus a good leaving group then? What are you effectively trading when you're doing an SN2 reaction? Yeah.
Electrons.
Always.
Where the negative is.
Where the negative is. The negative starts out on the
Carbon.
carbon, it ends up on a, which one's better at handling that negative? You guys get it? if, right? If you guys did this up here, right? You'd end up with an O with a minus charge. You're like, wait a minute, Dr. H. O is better at handling a negative charge than a C is. Correct? Yeah. Huh. Suddenly our world becomes a little bit more complicated too, right? Because we know that oxygen O is more electronegative, so it might logically make sense that the O is better at handling it. But it's not just, there's a couple things going on. First of all, that O with a negative charge, right, is different than this C that's sp hybridized with a negative charge, right? There's a little bit different going on there. The other thing that we're trading as we go through this is the bonds that are being broken and made. So if we go back to the reaction in green there, we break a carbon-iodine bond and we make a carbon-carbon bond. You guys with me on that? One of those is stronger. Okay? The carbon-iodine is stronger, the carbon-carbon bond is stronger than a carbon-iodine bond. Which means what? It's favored. Okay? Up at the top there, you have you would make a carbon-carbon bond versus a carbon-oxygen. Carbon-oxygen bonds are favored. So there's a couple different things going on. Why am I telling you guys this? There's one big idea that I want you guys to get out of it. The major idea is alcohols are not leading groups. Okay? OHs are not leading groups. Second of all, what I want you guys to get out of it is we are simplifying what's going on. And I can read your guys' mind. You're like, the hell you are, right? Right? It's pretty darn complex still, right? But there's other things that are working behind the scenes too. So sometimes we'll come across these reactions. We're like, I did my checklist and it didn't quite work out the way that I had intended. Okay? There are some other things going on behind the scenes that we need to pay attention to, or at least be aware of. Okay? Now, you guys are not chemistry majors. Okay? In fact, most of you guys are biology, right? Mute that for a second. I gotta tell you, no, I'm just kidding. No, I'm joking, right? So the point is, we're leaving some of these things out, right? If you guys were all gonna become chemists, then, we would spend a little bit more time kind of looking at these kind of things, right? So the big idea I want you guys to get out of this discussion is that alcohols are not good leading groups. And there is a rhyme and a reason for that. And somebody, I think Cole pointed out, he said, well, OH minus is a great base, right? Good bases do not make good leading groups. That's the other way of looking at it, okay? Weak bases make great leading groups. Is I minus a weak base? You bet. How do you know that I minus is a weak base? It comes from an extremely powerful acid, right? It's a delocalized negative charge. It's hard to get more delocalized than I with a minus charge, okay? You guys following along with us? Have we used any different explanations than we've ever talked about in the past? No, right? Remember, all I need you guys to know is everything, okay? And if you know everything, this class becomes easy, okay? Good. You guys with me then? So tell me what happens here.
Doesn't agree.
I wonder. those same series of ideas here. Start the one at the bottom. Build me a case. So leading group, secondary, not much steric hindrance, strong base, polar protic solvent. We can assume room temperature, concentration isn't specified. What's that all pointing towards? Go ahead. Say it loud so all of you of YouTube can hear you. Don't worry, it's like I said, it get like 12 views, so this will be good. There's like one of my videos that apparently is important. I don't know why, but I've got like 300 views.
Viral, Dr.
I know, yeah. Man, I can't wait to just rake in those pennies of, ad revenue there. I'm just kidding. None of this stuff is monetized. Although. Okay, good? All right, what happens up here at the top? That's right. Nothing seems to happen, right? Okay. Let's keep thinking then, right? Okay, tell me what your products are going to be. Nobody corrected me, huh? Sorry, we'll go back to this side. So first of all, what's LDA?
Strong base.
Extremely powerful base, right? Yeah. What else do we know about LDA? Yeah, extremely bulky. Okay. So, if we got a bulky base, that's very powerful. What's it gonna be pushing towards? E2, okay? So my product here is going to be set. This one I'm not throwing on purpose. This one I'm not throwing on purpose. Uh-oh. What in the world happened? Why would that be my major product?
Is it because it's terminal allocated?
That's what the product is. Why is that my product though? Yeah,
Less therapy.
exactly. To get to the hydrogen leading to that. You guys remember when we talked about Zaitsev versus Hoffman eliminations? Bulky bases will favor your easiest hydrogens to get to. And we can make these terminal alkenes. Got it? Do you guys catch the mistake there though that we just made? What did I do wrong in this one? Is SN2 favored at a secondary leaving group with a strong base?
No.
No. What's favored at a secondary leaving group with a strong base? E2. Can SN2 happen?
Yes.
Yes. But what will be my major product?
You do.
Just catch it. Okay. Don't get tripped up. It's one of the trickier ones. What happens at the secondary? Elimination will be favored. SN2 can happen. But the stronger the base, the more powerful the base, the more the elimination is favored. Got it? Why? Why would that statement make sense? The more powerful the base, the more the elimination is favored. Because what are the first reactions to happen? Acid base. So if you're a really powerful base, guess how you want to act? Like a base. And guess how you will act? Like a base. Got it? So if you're a really powerful acid, guess how you're going to act? Like an acid. When will you act like an acid? First. Got it? If you're a really powerful base, blah, 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 blah. You guys get the point? Identify strong acids, identify strong bases, make them act like strong acids. Did I make it act like a strong base in the first mechanism I drew there? No, I made it act like a good nucleophile. Can it act like a good nucleophile? Yes. Why? Why can it act like a good nucleophile?
Has a negative charge.
Hmm?
Negative charge.
It has a negative charge. Why else can it act like a good nucleophile?
It's not very sterically.
Uh-huh. Right? Whenever I ask you guys a question about SN2, just go ahead. Sterics! Just yell it, right? That's usually the right answer. Is that a very sterically hindered nucleophile? No. So can it still act as an SN2? Yes. Do you guys get the point I'm about to make? I hope so, right? How much SN2 is going to happen here? Probably none, right? There really won't be much of a competition there with SN2. LDA is too sterically hindered. Okay? What happens here? Oh, I wouldn't say that. I'll give you guys a hint. A reaction happens on that top. Stupid science, just when I think I know everything, right? I'll give you another hint. I just told you guys the answer about 30 seconds ago.
Sterics.
Alright, sterics is definitely part of this, but. What is LDA? Go ahead. It's a what? LDA is a powerful base, extremely powerful base. You guys got it? So what's reaction is gonna happen first?
That's two.
An acid-base reaction. You guys see it now?
Is the hydrogen on the oxygen the most acidic?
Yes, it is. What's the pKa of an alcohol? About 16. Got it? Is that a strong acid? Are alcohols strong acids? No. Are they acidic? Yeah, they're about as acidic as water is, right? Give or take. Is LDA a powerful base? Yeah. Is it going to find the most acidic hydrogen? Oh yeah. So what is going to be my answer here? What's going to be my product? O with a minus, right? And let me draw it out to get the point across, okay? There is protonated LDA, right? What functional group does this turn into? What functional group do we see there? An amine. What's the pKa of an amine? Kate looked it up 2 days ago, I think, 2 or 3 days ago.
13.
About 36-ish, right? Equilibrium favors what? Equilibrium favors the weaker acids. So the acid, what's the pK of an alcohol? pKa of an alcohol is about 16. What's the pKa of an amine? 36. Which one's a weaker acid? The amine. So which side's going to be favored? The side where the amine gets formed. You guys got it? Is it important to recognize your pKa's? Yes. Is it important to recognize that alcohols are acidic? Yes. There's a frog on the window. Very important. What's my product going to be? That's the question, right? There's two different mechanisms that are happening. So the question is really which one's going to happen fast. Yep. Always. Right? Those are always the fastest to happen. Yep. Darn it, I didn't trick you guys as much as I wanted to. I have to come up with super tricky questions on the exam. Alright. Okay, powerful base, it's gonna find the most acidic hydrogen. Okay? It's gonna find the most acidic hydrogen. Acid-base reactions, pretty much always going to be the fastest reactions to happen. Now, not to get too far into the weeds, although it would be a good thing to think about. Okay, ooh, I don't know how my writing skills suddenly disappeared. Does that make sense? What do you guys see in our product? Yeah. You got an O here. Is this still a good leaving group? Could this continue to react? No. So you guys get the point I'm making though? Could my product continue on in another reaction? Yes. Right? In fact, if we did try to do this in the lab, this would make a giant mess. Okay? It would make a giant mess. This right here could go on to react with itself. It could react with another starting material. It could react with another product. It could just continue to do other reactions. Don't get in the habit of, okay, there's my product. It magically stops existing and reacting. Think about what your product can do, okay? You have to start playing chess. Any of you guys, I don't really know how to play chess, so if there's one of you guys are experts, but when you do play chess, it's always, you don't think about just the next step. What do you think about? The step after, and the step after, right? You're always thinking multiple steps ahead. That's how we're gonna have to start thinking about these reactions here, okay? What else can they do? What could they do next? What is my product? Okay, my product, I see a strong base, a good nucleophile, I see a leaving group, blah, 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 right? And we start to see these things start to cascade off of each other, okay? The point I want to make is this. Alcohols are not good leaving groups. LDA is a powerful base. It is going to find a acidic hydrogen, okay? And that's going to be the first reaction that happens. Acid-base reactions are always going to be the first reactions to happen. Got it? Are you sure you got it? What's that?
How come on the other, on the other one in which on the OH and the,
This one.
yeah,
How come that didn't react?
yeah.
Yeah. It's a good question, isn't it? So what's the answer?
They kind of, because they're both oxygens, they're equivalent.
Their pKa's are very similar. Are they the same though? No. Will that O minus go after that OH there? The answer is, yeah, it will. But then it'll immediately go back. But then it'll immediately react again. And it'll go back, and it'll react again, it'll go back. It'll establish, let's see, what term could we use for that? Where the forward reaction rate equals the reverse reaction rate. It'll establish an equilibrium. And the equilibrium will have, one of those will exist with a minus, and the other one will be protonated. But because they're so close in pKa, there will be a preference for one over the other, but for us, unless I gave you guys the numbers, there's no real reason to it, right? Does that make sense though? So why is it different with LDA? LDA is way more basic, right? Way more basic than O with the minus charges. Does that make sense? That's a good observation, right? Important question.
Would there be a minor product in this one with an E2?
here?
Yeah.
It could, but it'd be very minor, right? Because acid base is gonna happen so fast. But there'd be a giant mess, is what it really would come out. I'm not gonna sit here, I mean, it'd be a good practice if you guys wanted to figure out what all the products could be, right? But it'd be just such a giant mess that, you know, I'd have to give you guys other information to really figure it out. You don't understand, Dr. H. In my lifetime, I want to see alcohol act as a leading group. Okay, fair enough, let's make it happen, right? So to turn an alcohol into a good leaving group, we're gonna have to change it, right? We're gonna have to change an alcohol into something that's good at leaving. What makes a good leaving group?
Handle a negative charge.
What do you mean by handle a negative charge?
So with a large, atomic radius.
Okay, well, are we gonna ever change the radius of oxygen? No, right? But what else can we do to handle the negative charge? Right, we could give it resonance structures, right? You guys with me on this? So if we transform an alcohol into a better leaving group, then guess how it's going to react? Like a leaving group. Have we talked about any leaving groups that have O's with minus charges on them? I'll give you a hint for that one too. The answer is yes. Wait, if we did. We did. Let's see if we can find them. Oh. Got it? It was literally a page up, guys. You can't remember that? Dr. H, that was 2 days ago. I can barely remember what I had for breakfast, right? No, right? But here we have O's with a negative charge that are fantastic leaving groups. So what's our job going to be? Turn an alcohol into a tosylate, okay? That's going to be our job. Once I turn an alcohol into a tosylate, it becomes a good leaving group. And how do good leaving groups react? Like leaving groups. Got it? So, how do we turn an alcohol into a leaving group? It's going to take an extra step in between there. Sometimes. Okay. And what we're going to do is add something called, or we're going to add this, I should say. Oh, sorry, we haven't learned that yet. Let me, a little bit of a fix here. There we go, that was fine. We put these things together. And if I put these together with an alcohol, what I will make, let me put some color with this, right? So red oxygen there, starting from the original alcohol. Okay. Good. They show you how this is done in the book. You guys can look it up. It's not necessarily a mechanism I expect you guys to do, although it's just based off of an SN2 mechanism. So you guys could do it. got a tosyl group here. So let's kind of abbreviate what's going on here. The other way you'll see this written is TSCl and pyridine. Okay. If we mix these together, we will make OTS, right? We'll generate a tosyl group from our alcohol using our tosyl chloride there. If we've got a tosyl group, now it's a fantastic leaving group. Good? Practically speaking for us, how's a tosyl group going to behave differently than a halogen as a leaving group? The answer is, it won't, right? Leaving groups are leaving groups. Tosyls are great, or excuse me, I should say tosylates are great leaving groups though. Fantastic leaving groups. But in terms of mechanism or any of that kind of stuff, they're going to behave the same way. Got it?
Why did the chlorine, where did the chlorine go?
Yep, the byproduct in this is your pyridinium chloride. So the pyridine is an organic base. It's going to pluck that hydrogen off of the alcohol and generate a positive charge, and the chlorine becomes its counterion. Cool. All right. Let's see. I can tell that it's Friday, and that you guys want to think. Right? I want you guys to play chess. Okay? You can't do this in one step. So show me more than one step to do this. First things first, right? We've got to change our alcohol into a good leaving group. So that in the second step we can do a substitution, right? Fortunately, we only know one way of doing that. And then second, we can come in with our sodium cyanide. You might see something like DMSO around. Okay? Now, what in the world is DMSO? DMSO is something as dimethyl, so DMSO, sulf oxide. So dimethyl sulfoxide. DMSO is a aprotic polar solvent. Okay? An aprotic polar solvent. Doesn't really participate in the reaction, but you guys might see it around in some of the reactions that you guys have in the book there, some of the examples that they give. There it is. Behold its magnificence, I guess. Okay? Cool. All right. That seems like a good stopping point since we don't have enough time to kind of launch into the next idea. But I will see you guys on Monday then. Make sure you guys please are following through and studying and doing practice problems and whatever you guys do. Because we're still not done with these chapters. There's still more we have to learn. So, this next exam has a lot of information on it, okay? So I'll see you guys next time.